Welcome to Embedded Edge, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on embedded systems technologies and products featured on embedded.com and through other AspenCore media publications. In this show, you'll hear both engineers and executives discuss news, challenges and opportunities for embedded systems design in markets such as automotive, industrial, aerospace and consumer. Here is your host, Editor-in-Chief of Power Electronics News and Embedded.com, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of Embedded Edge. So today the topic is AI, how AI is shaping the future of wireless system. We are diving into how AI native technologies are driving innovation in the next generation of wireless systems from 5G advanced to the next 6G. Our guest is Houman Zarrinkoub, Principal Product Manager for Wireless Communications at MathWorks. And he will share his expertise on why AI is critical for wireless engineering, the benefit it brings, and the step to overcome integration challenges. So let's discover how AI is revolutionizing wireless systems and empowering engineers to push the boundaries of connectivity. Let's talk with Houman. Hi Houman, thanks a lot for being here. Thanks a lot for coming on at Embedded Edge. How is it going?
Thank you very much. Everything is fine. We are close to Christmas time and family is fine.
Good. Where are you located, Houman?
We are in suburbs of a Boston area in Massachusetts, United States. Yeah.
Okay, good. So today the topic, as I mentioned at the beginning, is AI. So how AI is shaping the future of wireless system. So let's start with my first question about why AI native technologies, so next generation wireless standards, are becoming complex, even more increasingly. So could you explain why adopting AI native technologies is important, is essential for advancing standards like 5G, but not only, also 6G?
Yeah, as you can imagine, the wireless technology and industry, essentially as it evolves, the expectation of the end user is ever increasing. So not only you want to be connected, you want to have high bandwidth and high data rates, and the number of users go higher. And lately, the kind of users is not just a human being using a cellular phone. I mean, the cars of the future want to connect wirelessly, the assets in the industry. So the complexity is multi-level complexity, right? Mm-hmm. And the expectation is of the wireless system is a lot. So if you have an ever-growing user set and ever-growing applications, the main problem of wireless industry becomes allocation of resources. What do I give to which user at which time that matches his needs or her needs, as well as make sure I have the resources for everybody to share that finite resources. And that is where AI shines. AI is one of those techniques that handles multivariate and nonlinear systems, meaning multiple variables that determines the system performance, and nonlinearity. People come in, people go out, cars come in, cars go out. So that multivariate and nonlinear feature of wireless systems of the future, 5G, 6G, lends itself to AI being a necessary way to do that. The old ways of doing it based on averages and approximations are over.
Good. So let's talk about benefits of AI native systems, maybe in comparison with conventional solutions or approaches. So traditional wireless models have been used for years. So how do AI native systems improve wireless engineering compared to conventional solutions?
The conventional solutions will hit three problems that AI is trying to solve. One of them is customizability. I mean, the number of parameters that makes the solution optimal for you is just ever so increasing, and no conventional system can handle that. One of them is scalability. I mean, the number is huge, and at some point, the human-based systems cannot handle that. And then is robustness. What do you do when things go wrong? So these are the elements which are enticing people to go for AI native. And let me tell you the story of AI native that you may like. Usually, traditional engineering systems, a human being designs a model with parameters, and data comes in from reality, and the engineer fits the model with the actual data. Now, that's good, but because of the scale issues, because of the customizability, that model could be suboptimal. So AI native says, let the model be designed by data. That is the main point. Instead of somebody says, I think it's a Gaussian distribution or this distribution, that distribution, the AI native technology says, or methodology says, let data help you find the best model. And as the best model is found, then you apply parameters, you optimize it. That is something that is necessitated by those three things I told you: the scale, the customizability, and robustness. Those model-based stuff will start to fail if we don't embrace AI native approaches.
So, talking about designing AI native wireless systems, may you outline the steps, the main maybe steps involved in designing and integrating an AI native wireless systems?
So as I mentioned, that's a great question. So because data, which is the actual measurements from reality, leads to a model, and then model is optimized and then deployed. So the first step, of course, is data gathering, right? And data that we gather has to have lots of good properties to be ready to be used for AI native system. So we need large amount of data, right? I'm sure you heard that in the future we may have to use atomic reactors to to feed these data systems, because they're so large, we need actually dedicated power systems for them. Imagine how large the data should be. So the data has to be large, and Maurizio, data has to be representative, meaning that if the data only covers the usual cases and doesn't cover the outlier cases, right? Then you're designing a system based on just the best possible scenarios. You're ignoring the worst case scenarios. So you have to have enough data at the usual case, at the average case, plus standard deviation, and you have representative amount of data at outlier cases such that the system is not biased toward something. So these are the considerations as a first step: data, and representative data, which requires human supervision for label them. In this case, you have this data. In that case, you have that data. That's called labeling. So that's the first step. Then you have to embrace those optimized AI training algorithms. You need to have different architecture, convolutional neural networks or other architectures who actually can handle these data and train. And after you train, you have to plug the trained system into a real system. It's called integration, and make sure that the promise of AI is realized, meaning that this system can handle all the cases it hasn't seen before. So the data was trained on a different set of systems than the testing systems, and it can do a performance and verify and validate. And then you have to actually program that into hardware. So these 4 steps of data gathering, AI modeling, integration testing and validation, and deployment onto hardware are the 4 steps that we see our customers deal with AI systems.
And in terms of integrations, are there any challenges that engineers should face, or just as you mentioned in terms of model data?
So if you integrate your design system, right, into your final project,
yes,
and you didn't consider the typical and outlier cases that the system will see in your training, then this trained system, it's not a magical thing. The system is trained on data. If the data was inadequate, you have to be ready to go back and retrain your systems. So some of the challenges is, how do I retrain the systems? Reinforcement learning is one of the approaches taken, that if you create an AI system as an initial condition, can you make the AI system keep learning as new data comes in the testing and integration process? So we see a lot of customers are talking to us about reinforcement learning, meaning that as you deploy a system, integrate the system, let the system keep learning based on a new data. That's something that if people design it for a static condition, that's going to be a problem. So reinforcement learning and dynamic learning is one of those challenges you have to consider. As well as at some point, you say, okay, the main problem is this. Okay, this system seems to be working, but I don't know why it's working, Maurizio. Is there a human model that can explain this notion of explainability? Because if something goes wrong and you have a system based on data, how do you know the first module or second module or third module is not working properly? So you have to develop, as a human mind, a model that represents your data-driven AI native model. So these are the 2 challenges our customers talk to me about, is the notion of constant and dynamic adaptability and training, and explainability. How do I explain why it's working and when it's not working?
So let's talk about some real-world applications, some use cases, so compelling examples. So what are some of them in wireless communications where AI has proven transformative?
One of the areas, I work a lot with wireless communication customers, Maurizio, who are in the cellular business, meaning the base station talks to your cell phone, and we have this wonderful cellular connectivity wherever we are, right? So the cellular customers that I talk to are very impressed with the ability of AI to compress the data that is essentially overhead. You know, when you talk to your wife or I talk to my child or whoever, our voice, our video is the main data. But sometimes this channel has data for signaling, for control, change this, change that. If that signaling data, which is not the data that the end user uses, is big compared to the channel and occupies too much of the channel, then me and you cannot talk to our loved ones, right? So the overhead data must be compressed as little as possible, and the available resource allocated to the actual users talking to each other. So this notion of application of AI for minimizing the information back and forth between the base station and cell phone, right? It's called channel state information feedback. That feedback, keep talking to each other. You are giving me too much, you're giving me too little, do this, do that. That CSI, or channel state information signaling, being compressed without losing any information, is one of the areas that in 5G Advanced, in 6G, AI has shined. So using data, we can minimize the number of bits sent back and forth between base station and UE without incurring any penalties. So that's a transformative application of AI, I would say.
Nice. So, Houman, my last question in terms of what's next. So, as we look forward, just a look in terms of how do you envision AI shaping the evolution of wireless standards and technologies beyond 6G? So, what is your prediction, maybe?
Because of my job, I have to read a lot of papers of, my colleagues, my friends, smarter than me, as smart as I am, or whatever, on this topic. So the word that keeps coming up, my friend, in this beyond 6G conversation for AI is the word called digital twin. So imagine if you are communicating with somebody on the other side using a cellular phone and cellular technology. Your phone, right, may form a digital twin of your voice. We get used to it. I know what frequencies you have, Maurizio, and what frequencies you don't have. So if you have a digital twin of your voice in your cell phone, instead of sending everything you say without any modification, the digital twin is known and it can be communicated with the other side, right? And so you only send the information that is the minimum amount of information, not only for signaling back and forth, but even your voice, your video. You only send the stuff that is absolutely necessary. And that's why in the future, they say there's a digital twin of each user in the cellular structure, right? And this digital twin is constantly refreshed every time we use the network. And only if our digital twin, our avatar, our ghost, if we know what he's going to say, we're just going to not send it, just transmit the information. Only the new stuff, the innovation stuff, the stuff that we cannot predict is transmitted. Imagine how that is going to reduce the load on the system. Only the stuff the system cannot predict is transmitted. That is something that a lot of our wireless engineers are working on for every physical system, assuming a digital twin representation and using that as a first degree approximation of that physical system and only transmitting what we don't know. That is a very elegant solution that could come in 6G, 7G, and so on.
Nice. Looking forward to digital twin. Thanks
Absolutely.
a lot. And stay in touch with embedded.com. Thank you, Houman.
Thank you so much.
That brings us to the end of this episode. Stay tuned for more news and technical aspects about embedded systems design. If you are listening to this on the podcast page at eetimes.com or embedded.com, links to articles on topics we have discussed are shown on this page. Embedded Edge is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio, and the producer is James Eade.